Welcome to the podcast. This is Mr. White,
And Mr. Sadler.
and we're back to some equations today. Up until this point, we have been very specific. We have talked about left-hand rule. We're going to talk about that again today. We have talked about magnetic field, and we said in order to have a magnetic force, you have to have a field. So the field leads to the magnetic force. But we have not gotten into any great discussion about that. We have spent a lot of time talking about wires and the field and therefore the force of magnetism that is generated by a current carrying wire. So we're going to revisit these things today. Left-hand rule and wires.
Well, isn't the force that we're going to talk about today, isn't that what you feel when you crank the hand crank generator?
That's part of it.
Inducing a current?
What we identified in Chapter 6 is we just said, hey, that's this electricity, this electrical force, but really it's the electromagnetic force. I mean, we'll start to piece that puzzle together today. And then the other thing, so we're going to investigate this today, the magnetic force, and we're also going to investigate the single charge, which is a little different item or animal altogether. Wires are lots of charges. This is just going to be one electron at a time. So the first thing we're going to look at, of course, is the equation side of things.
The Active Physics Plus, it actually says, is there an equation that can describe this?
Of course there is. So the magnetic force, and I'm going to label this a little bit better than your book does, is equal to the current times the length of the wire times the magnetic field. All right, so some of these things should be becoming very familiar. Length of wire. So this is your wire equation for magnetic force. And the force itself is related to how strong the magnetic field is. So there's a very obvious relationship here. If you were to increase the current, you would increase the magnetic force. That, in turn, according to my other equation, would increase the strength of the magnetic field, which also increases the magnetic force. And then the more access to charged particles you have, the longer the wire, the more conducting material there is. That would also increase.
In the motor, the more wraps there are.
The more wraps there are around the coil or the aperture in the motor, that would work as well. So this is one equation. It's a very simple equation. It's not difficult to manipulate. Force is force, so it's still measured in newtons. Current is amps. Length is meters. Remember, the magnetic field is measured in teslas. The other side of things, so this is the wire side, is the charge side of things. What if a single electron or a single charged particle were to desperately float through a magnetic field? What would happen? And that would give off a magnetic force as well, because magnetism and electricity are related, as we saw in Section 1. And this would be related to capital Q times V times B. Well, B is not new. That is the magnetic field strength. Right, and I suppose I should write that up here. Measured in teslas. V is the speed of the charge. Now, a charge could be a single electron. It could be that simple. Or it could be a big chunk of a particle that has a lot of charge, has access to carry a denser charge to it. And that's what, tragically, Q represents. This is the electric charge. This is measured in coulombs. Speed is in meters per second. B is in teslas. And somehow that all works out to equal a Newton.
This sounds a lot like the experiment that Millikan did, charged particle to figure out the charge of an electron.
Right, and Millikan was he wasn't the first American to win a Nobel Prize, but he was one of the first. And you can actually view his manuscript at the Smithsonian Millikan did one of the famous cherry-picking data experiments. He knew what the answer was supposed to be, and every time he did an experiment he wasn't happy with, he would cross out pages of data, and he would actually circle the data points he wanted to write about, and he would write, use these. I believe he was based out of the University of Chicago, if I recall correctly. A different Millikan than Millikan University, but a notable American physicist, sort of put the United States on the map as a place to do good science. Because before that time, it was all the good science was done in Europe. And there's a lot of reasons why it transitioned to the United States, but Millikan showed that you could do solid science in the U.S. Now, unfortunately, as we introduce, we've talked about current, and we've talked about maybe the direction the charge or charges are moving, and we've talked about the magnetic field, but now we've introduced this third item. And this third item is the magnetic force. And so we're going to have to revise our left-hand rule, unfortunately. And this will not be the last time that we do this. Our rule for wires is good. We have no concerns about that. It is what it is. But our rule now for this single electron or this single charge carrier complicates things. Because in order for there to be a force on this charge, in order for the charge to move or change its motion, there has to be a force on it.
Right.
Well, what direction is that force going? So the thumb is still going to equal the direction
The current flows.
of current or charge movement. That's easy. The fingers are still going to equal the direction of the magnetic field. So what's happening here is this charge, if we have a single charge, it's floating through an established uniform magnetic field.
Different than the wire, sort of like a charged plate or something like that.
Right. And then the palm of your hand. This is the direction of the electric force. Right? If you're going to move an electric charge, gravity is not going to be a player here. Gravity is too weak of a force to influence anything with an electric charge, so the electric force is going to be responsible for the movement. Now, as you use the left-hand rule, it's important that you read everything carefully, all the details in the problem or all the details in the diagram. So what we're going to do for you is we're going to look at number one, and we're going to try and apply the left-hand rule accordingly. So while you're listening, get your left hand out and relabel, thumb is the direction of the charge, fingers is the direction of the magnetic field, and palm is the direction of the electric force. Now there is another method, and it's very similar. You could do thumb, pointer finger, and then you could have your three fingers, middle, ring, pinky, point up. And so this could be current or charge direction. This could be magnetic field, and then this could be the electric force. So what this shows is that everything is 90 degrees to each other. So the current is at a 90-degree angle to the magnetic field, and the magnetic field is at a 90-degree angle to the electric force, and the electric force is at another 90-degree angle to the current. So whatever makes you happy. Mr. Sadler prefers this method. I'm going to go with your textbook method, but both work. I like this because this shows 90 degrees everywhere. So I'm looking on page 740 of your book, and it talks about a magnetic uniform field. And they do a much nicer job of drawing this than I ever will. Okay, and they're telling me that a negative charge is going to the right through a uniform magnetic field that is into the page. So I've got to situate things so that my left thumb is moving to the right.
Because the current's to the right.
Okay, that's the direction of the charge or the current. My fingers, or even just my pointer finger, is down into the page because that's what it tells me, right? It says be into the page. You can't see me right now, but I'm actually doing the left-hand rule as I'm talking. And then my palm or my other three fingers are pointing towards me, Now, so with respect to the page, the electric force then, according to the left-hand rule, is down
Correct.
the page. Right?
Correct.
That's it. Nowhere in the use of the left-hand rule can we talk about the magnitude of the field, the charge, or the force. That's
Right,
what the
it's just
equation
showing the direction.
for. Yeah, it's just showing directions. So, Mr. Sadler, would you like to try and talk us through the second one?
I'll try.
Okay.
So the current is in what direction? The arrows show going up, right?
The current is to the right. So we
Okay.
see our negative charge, and there's an arrow pointing to the right.
So it's the field that's up and the current's to the right.
That is correct.
Okay, so my left thumb is pointing to the right.
Okay.
Okay, and the magnetic field is up.
Okay.
Current field.
So the electric force.
So if I point my thumb to the right
Okay.
and I point my fingers up like the field, then my pointer finger points down.
And so the electric force
Should be down.
should be down. So electric force is it is down, but into the page.
Right, when the book is sitting in front of me, right?
And so once again, think of the 90-degree thing. Everything is 90 degrees to each other when you're doing that. All right, and as a result, you have kept the left-hand rule intact, and everything is kosher.
Right.
The last one, so let's draw the electric charge first and color code this a little bit. That is, the electron is moving up.
Okay.
The magnetic field is uniform and to the right. So thumb is up, pointer finger is to the right, palm and other three fingers are pointing up.
Right.
So the electric force
Is out of the page.
is out of the page. And I have established a method for determining the direction of these items.
Correct.
So this is an addendum to our left-hand rule to account for the electric charges, the singular charges, rather than the current.
Right.
When it's all isolated and housed in the wire, remember the field wraps around and it's not perpendicular. It's not an established uniform magnetic field. So what we would like you to do is to investigate number 2, and it wants you to find the force on the electron. All right, and they give you some speeds and charges and some other things. And there's a little discussion at the end, so I'll let you take some notes on the V is equal to the electric potential energy over the charge, and see if you can make some sense of that.
So for 2, I'm just going back to the 2 formulas right at the beginning.
And you're going to have to pick one and do it right, and then do a little reading beyond that.
Okay.
So I think that wraps it up. Signing off, this is Mr. White.
And Mr. Sadler.